Hello there, Mr. Sutton bringing you the AB Calculus 6-6 homework answers on motion and position. For this problem, we have a particle moving along the x-axis so that at any positive time here, or greater than or equal to 0, its velocity is given by this v of t cosine 2 minus t squared function. And they're telling us the position of the particle is 3 at time 0. Based on that, what's the position of the particle when its velocity is first equal to 0? So at some point we need to figure out, when the velocity is 0, and whatever that time is, we're going to have to plug that into something that gives us the position. So let's take it one step at a time. Let's figure out when the velocity is 0. This is a calculator question, so we're just going to take this v of t and set it equal to 0 and solve that on Desmos. So here I am on Desmos. Let me take v of t and enter it in there so that I have it. So that'll be cosine, and then we've got 2 minus t squared, and that's a crazy function there. Now, if you're looking at these answer choices, it doesn't actually tell you much because these are all positions, not velocities. But if we're looking to see the first time that the velocity is 0, it's going to happen close to the origin here. Let's just zoom in a little bit here. And if we zoom in, take a look at this spot, we see that it's about 0.655. And I'm just going to save that, and I'm going to call it A. So let me go back here, and let me cut and paste that, and we'll store that as A just so I have it for later, because I need that time. So there is my graph that I just did. Again, I'm going to call that value A. And now, in order to find the position at time A, I need to do the initial position plus the displacement from that. So I can say that x of a is equal to, and my position was 3 at time 0, so x of a is going to be 3, that's x of 0, plus the integral from 0 to a of v of t dt. So let me go back now and plug all that in the calculator. Let me just move this so I can see. So let's go down here. We're just going to do 3 plus integral int from 0 to a, got that stored value, and then v of t dt, there we go, and that's all coming out to 2.816. Is that one of my answer choices? It is, choice C. On this calculator problem, for time greater than or equal to 0, the acceleration of a particle moving on the x-axis is this a of t, t plus sine of t function. And at time 0, we know the velocity of the particle is -2. We want to know at what time the velocity of the particle will be 0. So our strategy for this one, we are going to come up with a formula for the velocity based on the acceleration and this initial value. So we're going to have to do a little bit of diffie-q for that. And then we're going to take that velocity formula and set that equal to 0 using the graphing calculator. All right, so first let's get our v of t function. So taking the antiderivative of acceleration to get velocity, we have v of t equals, and antiderivative of t, that's going to be 1/2 t squared, plus antiderivative of sine, that's going to be negative cosine of t. And then we have a plus c that we can't forget about. So for that plus c, let's go ahead and plug in our initial value, our initial condition. So at time 0, the velocity is -2. So we can swap out v of t for -2, and all these t's we can turn into zeros to plug in the point 0, -2. So 1/2 0 squared is just 0. That's kind of nice. Cosine of 0 is going to be 1. So we have -1 plus c equals -2. And if I add the 1 over to the other side, now I'm going to have c equals -1 for my final c value. So plugging that back in, we've got 1/2 t squared minus cosine of t minus 1, and we're going to set all of that equal to 0 and solve that on Desmos. So let me go there and do that. So let's see here. Let me just do 1/2, and instead of using t, I'm going to use x squared because I haven't actually named a function with t in it on here. Minus cosine of x minus 1, and we want to know where this equals 0. So let me zoom in here and see what that spot is. It looks like that's about 1.478. So there's what I got on the calculator, time 1.478, and that rounds off to 1.48, which matches answer choice B. On this calculator-based problem, we have a particle moving on a line so that the acceleration at times greater than or equal to 0 is given by this a of t function. If particle's velocity at time 0 is 5, we want the velocity of the particle at time 3. Well, this is a fairly straightforward FTC type problem. We just need to take the initial value of 5 and add the integral of acceleration, which will be the change in velocity, from times 0 to time 3. So let's go ahead and just show the setup on this one. So we're going to have 5, that was our initial value, plus integral from 0 to 3 of a of t dt. And now I have to do all this on the calculator. So go into Desmos. First step is going to be to actually enter my a of t function in here. And let me make a fraction. We'll do t plus 3. And then we'll do, this is a square root, sqrt, of t cubed plus 1. So there's a of t. Now I just need to do 5 plus integral, int, from 0 to 3 of a of t, and I have to write in dt as well. And that gives us 11.710, which matches answer choice E.
On this problem, we have a particle moving along the x-axis with an acceleration given by the graph here from 0 to 1 for time. And at time 0, they're telling us our velocity is negative 1/2. So based off of that, which of these statements has to be true? So particle passes through x equals 0 for some time between time 0 and time 1. We have a graph of acceleration, and we're making judgments about position. We might be able to if they told us the initial position, but they didn't tell us where this thing was starting. So although our acceleration's positive, I mean, we could try figuring out the velocity, but any of that is not going to help us if we don't know where we're starting. So because we don't know the initial position, choice A, we can't actually conclude that one. Choice B, velocity of the particle is 0 for some time between 0 and 1. So our velocity is initially negative 1/2. And this acceleration curve here, this is adding velocity to this because this is positive acceleration. So the question is, do we add enough velocity to go through 0 on this thing? Well, looking at the area under this curve, we don't know the exact formula for this kind of curvy shape here, but we can draw a triangle that's less than that from here down to here. And this triangle has an area of 1/2 base of 1 times a height of 1, so an area of 1/2. And clearly, we have more empty space underneath the curve. So because we're starting at velocity negative 1/2 and the area under our acceleration curve is more than 1/2, we can say yes, velocity of particle is going to have to be 0 somewhere in between time 0 and 1. Now the other piece of this that we kind of glossed over is we know we have to go through a value of 0 versus just kind of warping from negative 1/2 to some positive value because the velocity function is continuous. How do we know velocity function is continuous for this? Well, the acceleration function is definitely continuous, which means the velocity function is differentiable and thus continuous. So the intermediate value theorem states that because we're starting at negative 1/2 and we're ending at, well, more than 0 because we're adding more than 1/2, we're going to have to go through 0. Looking at some of the other answer choices, in case that wasn't enough to convince you just yet, choice C, velocity of the particle is negative for all values of t between 0 and 1. Well, clearly it isn't. We just proved in part B, or at least answer choice B, that we're adding more than 1/2 to that value. So that means that we're going to end up with at least some positive values for velocity. On the choice D, velocity of the particle is positive for all values. Well, that can't be the case. I mean, we're starting negative and it's a continuous velocity function, so it has to go through other negative numbers to get to positive land. And now then there's choice E, velocity is less than negative 1/2. Well, this is really false. I mean, we started at negative 1/2 and we're adding positive area. So that's going to at least make it more than negative 1/2, even if it never becomes positive at all. So by process of elimination, choice B then. For this problem, we have the velocity of a particle moving on the x-axis given by this velocity formula. If the particle is at x equals 4 at time 0, we want the position at time pi over 2. Well, that's an interesting time, but if you look at the type of function involved, it makes sense. So how do we figure this out? Well, the velocity, or rather the position, at time pi over 2 is going to be equal to the position at time 0, which is 4, plus the integral from 0 to pi over 2 of our velocity function. So this is going to be equal to 4 plus, well, now what's the antiderivative of the velocity function here? So antiderivative of sine is negative cosine, but we have a 2t inside, so we're going to have to divide by that tail of 2. So negative 1/2 cosine of 2t then, evaluated from 0 to pi over 2. So that's going to be 4 plus all of this with pi over 2 plugged in, minus all of this stuff with 0 plugged in. So that's 4 plus, and now this is really cosine of pi, which is going to be, let's see, negative 1, but we have a negative half times that. So that ends up being positive 1/2 for that first bracket there. Over here we have, let's see, cosine of 0, which is 1. That becomes negative 1/2, but this negative outside makes it positive again. So we have 4 plus 1/2 plus another 1/2, which all adds up to 5. Choice D. For this one, we have a particle moving on the x-axis with an acceleration given by negative 4 sine of 2t. If the velocity of the particle at time 0 is going to be 7, and its position is 0, we want the position at time t for any t value. So we want the general formula for x of t. So we're starting with acceleration. We have to get to position. That means we have to go antiderivatives 2 steps. Now, it's really hard to do this with FTC, so we're going to use a diff-EQ approach instead on this one. So I'll start by taking the antiderivative of my acceleration equation up here. Antiderivative of a of t is going to be v of t. And on the right side, antiderivative of sine in general is negative cosine, and we're dividing by 2 because of this 2t inside. So that's going to be positive 2 cosine of 2t plus c1. We'll call it c1 because we're going to have another constant later on. Now to find my actual velocity formula, which I'm going to need if I want my position formula, I'm going to plug in 0 for t and 7 for velocity because of this initial condition here. So we have 7 equals 2 cosine of 2 times 0 plus c1. Cosine of 0 comes out to 1, so that's just 2 plus c1. Subtracting 2 from both sides, we have a c1 value of 5. That means my velocity formula is 2 cosine of 2t plus 5. Great. Let's go ahead now and find the position formula. So that's going to be x of t if I take my antiderivative. And antiderivative of cosine is sine, divided by 2 now because of that 2t inside. So we end up with 2 over 2, or just 1 sine of 2t, plus 5t plus c2. Now we have to find the value of c2 by plugging in our initial condition for position. So we have 0 going in for x over here, and that's with an input t value that's also 0. Sine of 0 is 0, 5 times 0 is 0, so we end up with c2 equals 0, which means x of t really just equals sine of 2t plus 5t plus 0, or just with no plus anything at all. And that ends up being choice A.
For this calculator-based problem, we have a particle moving along the x-axis with a velocity given by this v of t function and a position of x equals 1 at time 2. Based on this, we want the position of the particle at time 4. So we're just going to use our fundamental theorem, and we're going to take this initial position of 1 and add to that the displacement between times 2 and time 4. So that's going to be the integral from 2 to 4 of this v of t function here. So this is what I'm going to have to do on my calculator. Let me go ahead and execute that now. So let me first enter v of t in Desmos. So we have v of t equals, and I'll do a fraction, 4 over t cubed plus 1. And now let me just do my integral. So we have 1 plus int integral from 2 to 4 of v of t dt. and that comes out to about 1.353 if I round that off, which is going to match choice C.
For this problem, we're going to be using this table here, which tells us the velocity of some particle moving along the x-axis at various times. And we're told that we have a differentiable function v. And let's see, x is measured in meters, time in seconds. We'll have to include that when we come up with our answers on these problems. And finally, position at time 0 is 7. That'll be important too. But for our first part of the problem, we just need to estimate the acceleration of our particle at 36 seconds. Well, acceleration is the derivative of velocity. We don't know the exact velocity formula, but we can find the average rate of change of velocity to at least estimate the acceleration. So to estimate the acceleration at time 36, I want to find the average rate of change over an interval that includes time 36. Probably the smallest interval is the way to go on this. So I'm going to pick the interval from 32 to 40. So I'll say that the acceleration at 36 is approximately equal to the following. So I'm going to have v of 40 minus v of 32 over 40 minus 32. So that's going to be 7 minus negative 4 over 40 minus 32. And I could stick the units on this since it's all constants at this point and just call it a day. But if you actually calculate it out, this is, let's see, going to be 11 over 8. And that's going to be meters per second squared. On this problem, we want to explain the meaning of the integral from 20 to 40 of v of t dt in the context of this problem. So that's the first part of this. If I'm taking the integral of velocity, that's going to be the total change in position, or the displacement, of our particle. And this is going to be in meters because the velocity was meters per second, so meters. And also include the time interval. So this is from time 20 to time 40 seconds. So from 20 to 40 seconds. So we need each piece of this to get full credit. Units, time interval, and what it actually is. Now the next part of the question, use a trapezoidal sum with 3 subintervals to figure out that integral that they just talked about here. So be careful. We're only going from 20 to 40. So these are the only 4 sets of numbers we should be looking at. So I'm going to have, let's see here, base 1 plus base 2, so negative 10 minus 8 over 2 times an interval length of 5. And I'm going to say that this integral of vt dt is approximately equal to, because I'm approximating, I'm not giving the exact value. Next, we're going from, let's see, negative 8 plus negative 4 over 2 times 7 for the height of that trapezoid. And finally, we have negative 4 plus 7 over 2 times 8 for that interval length. And if you put meters on the end of this, you're done. You could actually simplify this if you wanted to. So let's see here. This is going to be negative 9 times 5, so negative 45. This next one, this is going to be negative 6 times 7, so minus 42. And this last one, let's see, 8 divided by 2 is 4. We've got 4 times 3, so that's 12. Adding all this up, this is negative 87 plus 12, so negative 75, and again, that's going to be meters. On this problem, for 0 to 40, must the particle change direction in any of the subintervals indicated by the table? So identify the subinterval and the reasoning. So when we're asking for a change in direction in the particle, we're asking where the velocity changes sign. And we can clearly see, just looking at these numbers here, our velocity is going to change sign somewhere in the interval of 8 to 20, and also, if you look further down, the interval from 32 to 40. Now, we don't know exactly where in those intervals it changes, but clearly, if you're starting positive and ending negative, somewhere in here you changed from positive to negative and vice versa over here. So that means that our particle must change direction on those 2 subintervals. For this last part, suppose our acceleration is positive on the interval 0 to 8. Explain why our position at time 8 has to be greater than 30 meters. So let's talk about the position in general. We're starting at x equals 7 at time 0. So our position at time 8 in general is going to be 7 plus the integral of x prime, or v of t dt, from 0 to 8. Let's talk a little bit more about what this v of t is doing, because we don't have a formula for it, but we do have a table with some values. Now, in general, we can't really assume we know anything about what's going on between time 0 and 8, in between this v value of 3 and v value of 5. But here's the key. Here they said the acceleration is positive. So the velocity's derivative is positive on the interval from 0 to 8. Since we start with a velocity of 3 at time 0, that means the velocity has to be at least 3 across this whole interval. In fact, the acceleration is positive, so it's going to be greater than 3 for most of this interval. But we can say our velocity is greater than or equal to 3 at the very least on the interval from 0 to 8. That means we could rewrite this stuff as x of 8 equals 7 plus integral from 0 to 8 of 3 dt if we wanted to, or we could say that this is greater than or equal to the 7 plus integral from 0 to 8 of 3. Now the integral from 0 to 8 of 3, that's just a rectangle with a base of 8 and a height of 3. So this is essentially 7 plus 24, which is going to give us 31 meters. So this is the lower bound on what our position could be, and that's greater than the 30 meters they talked about in the problem. So we've met our burden of proof by showing this.